start from a node and traverse the space, stop when the desired node is found. Now, this one you see is similar for a solution space search and a state space search. The definition of what a node is what differentiates the type of search. And also, if it is a solution space search, then there is no fixed start node.
Hmm.
So we said water jug can be posed as a can be posed as a solution space search. Now I can ask a question: is there a state where all three values, the water in the jug, are prime numbers? Then you start from some state and then keep transitioning until you find a state where the values are prime numbers.
Hmm.
That is solution space. In this case, every node is a solution.
All
If I
right.
pose a question, start from 800, given this state, start from 800, and can you achieve 440 and tell me how to achieve this?
All right. So the plan of how you're going, so the whole like configure the last one, so you're getting all the details, and in solution, you're just getting a yes or a no.
Yeah, yeah, exactly. So
All right.
does such a
Okay.
thing exist is one thing. And tell me how to achieve this. Is a
All
state
right.
space search.
Okay.
Okay.
Thank you, sir.
And yeah, sure. So now search question was, is hill climbing used for solution space search or state space search?
A solution space.
No, no, I asked about iterated hill climbing.
Still, it would be a solution space because it's basically getting like from all it's trying to pick the global. So it's a better version where it's randomizing and it's get still it's going to get a
Yeah,
solution
but
only.
if you remember, somewhere in the lectures we had a block solve problem, which we tried to solve using hill
Yes,
climbing.
sir. Yeah.
So that was a state space problem. You're given a configuration and you want to go to a new configuration.
So it can depend on the problem that we are tackling.
Correct. So hill climbing can happen in either of the two kind of spaces, but iterated hill climbing, the reason I asked was as to what are those randomized starting points. It's not as if somebody has given you a starting point. You are allowed to start from any place. So, for example, these numbers that Bhaskaran has written here, uh, those are presumably heights on a
Hmm.
contour map. You could start from anywhere and hope to reach the top. Nobody's telling you start from a particular location. So you
Yeah.
said that answer initially, which is that you can start from random places, but that's possible only in a solution space search problem because there the start state is immaterial.
All right. So we can, it depends on the problem. That's the answer because it
Yeah.
depends on what kind of problem we are tackling and then who is asking the question is the answer.
Does anyone have questions on the other topics? I'm the only one who's asking questions here. What about simulated annealing?
Currently, I'm at week 3, so I that's why I'm not able to ask any questions.
So do you have any questions from week 3 then?
Yeah, so beam search, I was I got stuck somewhere in beam search, and basically the difference that are there in beam search and best search. So as what I understood is so and then hill climbing also. So all the implementation wise they all seem similar. So for hill climbing, I have some value at each node. It can be Manhattan distance for the problem of 8 bold tiles. Uh, so and based on that, I will go to the. I want to minimize that Manhattan distance of the correct places of incorrect places. So I can use hill climbing, and then beam search again I can use, but there I can have more than one nodes to select as a best node. So and then so here I'm confused. In best search also we can have more than one nodes, and then in beam search also we can have more than one node. So the difference I was unable to find.
So what did you say? In best first search also we have more than one node.
Yes, yes.
Well, let's start with best first search. You maintain an open list and sort it based on the heuristic value and choose one node and test whether that's a gold node or not. But you keep all the other nodes in open, so it maintains that complete open, so it's a global search. Global in the sense it will it will always keep the solution. It will always keep the states that are part of the space. In hill climbing, you throw away the other nodes which were candidates and keep only the neighbors of the current node.
Okay, so it is basically affecting the memory. All other things are remain.
Yeah,
Is it
exactly. The
what
main advantage of
is
hill
there?
climbing is memory. What Beam search does is that instead of just looking at one candidate, you can look at some B candidates at any given point. So again, from a computer scientist point of view, the memory is still constant because you're only looking at B nodes. It's not something, at every cycle you are looking at B nodes. So it also works with constant space, but it has a greater chance of finding the solution because you are looking at more than one candidate, I think. So that's the idea behind Beam's search, I think.
All right, all right. So if in beam search I only go and look one candidate, so it will become just like hill climbing.
Yeah, exactly.
Okay. And then in the difference between hill climbing and best first search is so I'm throwing the data that other than I'm keeping some candidate nodes and then throwing other nodes in hill climbing. But in best first search, I'm considering everything. I'm not throwing anything.
Exactly. So in best first search, all the candidates that you have generated, you keep them in the open list and keep inspecting them one by one in some order based on the heuristic function.
Hmm, hmm.
In hill climbing, you only look at the neighbors of the current node, which is
You
also
can
what you do in taboo search, and you also look at simulated annealing, which maybe you have not yet seen, but that's part of week 4 of week 5, week 4, I think.
yes, sir. See, observe that hill climbing is not maintaining an open list here. There is no open or closed. So it's both are absent, right? Hill climbing is not maintaining these things. There's no open list and there's no closed list. It only maintains a single node that is the best node, best neighbor of the current best. This is the current best, and if this is the current best, and there are neighbors one level, one hop away, and of this, say this is the best. So let's say this is best ever, and this is n. And now search moves from if say the value here is 5 and value here is 10 in terms of heuristic value, then search would move and the best ever would become 10 now on the next iteration. So when it goes back, you're moving from 5 to 10, and now you're going to expand 10 and look for better values here. Say you get 12, then you would move to 12. So it's, and this would become best ever, and this would become n. So it always remembers only one node, and there is no path information stored here. The algorithm given here, it cannot reconstruct path. It simply drives straight down to the goal or to the minimum uh, cost node or maximum cost node, depending on whether it's a minimization or maximization problem.
All right. So in that way, let's say for a real solution exists which goes through the path that is which is going through the node that is, let's say, left from this node that has value 12. So but it will, hill climbing will find the 12 the node that has value 12, and it will throw other nodes. So that's why sometime it might not be possible to find the correct solution from hill climbing.
Yeah, if this say the solution is 100, so this is where we want to drive at, and say this becomes a dead end, it's a leaf, no more path,
Hmm.
and it is 6 here that finally leads to a solution. Now hill climbing has no way of. See, these are all, like I say, they are. This course, sir, discusses fundamental methods, the basic methods. Now you can mix and match and construct a hybrid to solve real life situations, real life problems. So you can augment hill climbing with uh, a closed list so that you can reconstruct the path, or you can maintain a path itself here. So all those additions you can do when you want to solve a problem in the industry. But there is no hard and fast rule that hill climbing should be implemented exactly the way we have said. But there are core ideas in hill climbing, and that will not change. If you want to call something hill climbing, and its basic framework, the spine should have a certain form, and that form is what is shown here. The skeleton is shown here.
All right. Thank you, sir.
A question that I asked in one of the live sessions is, does Sir discuss in his lectures a state space where a move is not immediately a move may not be immediately reversible, meaning it may be one directional, but eventually you reach some state and then come back to this state. Does Sir discuss a state space like this?
Not sure, sir.
I mean, are you guys watching the lectures?
Yes, I watched till week 3.
Okay. What are the state spaces he discusses? I mean, apart from the toy examples where he takes an abstract graph, says yes, and then goes A, B, C, not that kind of problems. Something that is practical.
Just like solving that 8 pole tiles.
Okay, solving the tiles. Okay, that's a nice practical problem. Okay. Okay. In that state space, do you see the state space having uh, a property like this?
If we, I think we can see if let's say only one move is allowed at one time. So uh, 4 getting close next to some value, let's say 3, it may not be possible in one move, but in after 4 5 moves it can be possible. So, yeah, so here let's, for
Sorry.
example,
And the remaining tiles are there, so I'm not drawing all the tiles. So these are the 4 possible moves.
um, yes, so here let's say for example I want to make 4 going uh, closer to, or closer to 2. So it is possible in the last node here, but it can be somewhere, means some configuration that is not possible in uh, one change, but in some multiple, after multiple changes we can make it possible. Is it what this directed graph is doing?
Yeah, directed graph is you can go one way and you cannot, undo the move.
Hmm.
The rabbit crossing puzzle is one such where you cannot undo a move. The right rabbits, the hop
Yes.
to the right and left ones hop to the left, and they can't hop back. So once they reach a state, there's no way they can go back to the old state. But in this state space, is it possible for us to immediately backtrack a move, immediately undo a move? That's in when humans are playing, not while running an algorithm. When let's
Yes.
discuss at a human level.
Yes, I think, yeah, it is possible.
So is it possible for all moves, or is it only possible for few moves?
I think for almost means for all these configurations.
Yeah, for any board
Yes.
question I'm giving, and given a, would say, the question is something like this: if Move gen. Let me write. Okay. Move gen as mg. So move gen of A is equal to a list of say A1, A2, dot 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 an. Then is it possible that move gen of AI, one of the A's, contains A as one of the elements? So this is a definition of a move that can be undone. So I can go from state to say A5, and the next move I can come back to A.
Uh, yes, sir. As for human point of view, it is possible. I can again make it move it, reverse the process that I did previously.
Yeah. So which means the move here you can undo it. So
Yeah, but that case, that example, that is a rabbit example, we can't do that
hmm,
because once a rabbit, there is a rabbit which is always going to go to left, right. So after moving to right, it can't move to left. It is only going to move right.
okay. So those are the kind of properties. So those properties you must try and understand for a given state space, and you will be able to write an optimized version of algorithms presented here. So the idea is you must understand the underlying property of the state space, the graph property. Some of the simple ones are is a more reversible, or
Bhaskar,
every move reversible.
Bhaskar,
Yes, sir.
I don't think you are looking at the chat. So,
Uh,
Garima has some questions on implementation, how to implement some of these things on the chat. Garima, would you like to just ask it directly to on
Yeah.
the?
So, I was following Deepak sir book, which is very like extensive on the courses that you're teaching, and it's very good. But problems like you have written that we have to write code, and even in the upcoming weeks, I heard that you'll be giving a programming assignment. So, to prepare for that, to convert the pseudocodes that have been given to us into Python code, I was trying to do that and go about it. So, with the PDSA that we learned earlier. So how they dealt with DFS, BFS was through adjacency matrix list and as well as taking edges. So what's the best approach to basically convert the pseudocode into coding, and is there a better way to go about it? Can you suggest how we can start by doing that?
okay. See, the algorithms presented here in this course, they convey the basic idea, the basic concept. Okay. The implementation is not the focus in this course. Okay. Having said that, now if you want to solve a real world problem and you want to say it is a state space, it's a planning problem where you have an initial state and you would like to know how to reach a certain final
Hmm.
state, then depending on the size of the problems, if you take adjacency matrix, is what is the branching factor in the state space? Is it
That's
dense?
definitely not a good solution to go by.
Then it's
Adjacency
not a
lists
good
are
solution.
better, definitely. Yeah.
Yeah, exactly. If the branching factor is low compared to the number of
Hmm.
nodes in the state space, obviously adjacency matrix is not
The
a good.
space complexity would shoot up exponentially more.
It would.
That's, yeah, I understand.
It
Yeah.
would. Okay. So that is not a good choice. But if it's a very dense graph, then probably adjacency matrix is good. Otherwise, maintain edge lists or adjacency lists for every node, not a
All
matrix,
right.
right? So
So we can have edge nodes and then we can call moves in again and again.
yeah, that is one
And
way of doing it. Yeah.
Because
So you have,
what I was doing was I was taking two approaches. First, I was tackling the list, and then I was creating the adjacency list out of that. So adjacency list is the move gen itself. So the move gen would be taking out of that dictionary the letter or the alphabet or whatever it is, and then returning the list of the move gen, the neighbors of that node. So
yeah,
that's how I
if
was
you are,
going about
yeah,
it.
if you are going to, if you want to implement the abstract problems that Sir discusses, the graphs, yes, adjacency list is a good approach. Like you said, adjacency list itself is the move gen
Yeah,
in
yeah,
that case. But if you want to implement the rabbit crossing puzzle, then you don't have the entire graph with you to start with.
true that.
You
Yeah.
have the start state, and you have to develop a move gen that given any state that it obeys the rules of the game, and then it generates all possible one hop, it is one hop, one length states, and
Hmm.
it returns a list of states. So you will have you have to write this function that says move gen, and it takes a state, use Haskell notation, and then it'll give you a set of states. Set. Going to give you a set of states. So you have to develop this function
Hmm.
for each problem, right? Now the
Correct.
in terms of implementation, now you have to see how to implement open. What data structure is good for open? What is good for closed? Okay. In extreme
Yeah.
situations, you may be able to get away with bitmapped indices.
So, but are there any resources to practice coding? Because even on the internet, like for PDS, there's a lot of resources on lead code and everything to practice. But for AI, for good old fashioned AI that we are being taught right now, there aren't any much resources I can find like to code and practice to get the concepts in the head. Like I understand Deepak sir explain the algorithm very well, and with the book it's really helpful. I can understand, but coding is a different thing, so I want to know the coding part as well.
It
So
really
are
depends
there
on
any
the
suggestions?
problem. Yeah, I mean, we don't. I have not used any framework. I've not come across any framework, but I've seen a lot of good demos from other universities
All
uh,
right.
of algorithms. Okay, and otherwise, I don't know. I have not seen a framework. So.
All right, okay, sir. Thank you,
So,
sir.
yeah, in terms of what programming assignments we would give, I think there's a TSP tournament that we conduct. So a TSP problem will be given. So you have to write a program to find the optimal tour, and whoever
Hmm.
finds the best optimal tour. I mean, finding the optimal tour is a hard problem. So you have to
So
use some
basically,
heuristic
we need
approach.
to have a grasp over the algorithms, implementing them as well as the DSA. So DSA is a stronghold as well over here in order to solve
Yes.
it.
Yes. In order.
All right.
Yes. And then the
So
best
the
tour wins.
implementation, can we have a coding session? Like, is it possible, like, even though there would be very less people, is it possible that we can have one coding session for people who are interested for AI only?
The problem is so simple. Most people, I mean, given that online degree
Algorithms
people
are
have
simple
gone through.
because it's still like it's some are understandable and it's some are intuitive as well, but like coding through it is the what I'm struggling through. Is it? If it's not possible, then it's okay.
Yeah, we can think about it. We can see if there is a slot where we can do such a thing. See, if your first line of attack should be forum. So ask the question in the forum. See if it can be addressed. I can point to resources. a general discussion. See, since it is a competition, I don't know whether people want to discuss their approach and strategy
True
in
that.
forum or in an open
Yeah.
live session. So it's a competition basically. It's not a tournament, it's a competition. So the best tour wins.
So
And you
these okay, sorry.
yeah, yeah, go ahead. So,
So these algorithms that we are studying are symbolic AI, correct? Like, is my understanding correct for this?
you can use it for symbolic, I mean, theorem proving. Theorem symbolic
Yeah.
is theorem proving is symbolic, right?
Yeah.
Yeah,
So
it is
basically,
applicable there.
like in the coming from what I've heard 2, 3 years back, like there's a new approach of combining deep learning with symbolic AI. So basically, the neuro symbolic AI. So you need to actually know how to code and then merge with deep learning to get the objects and feed it into the symbolic AI programming and merge the two fields together to get the best out of it. So how can we go doing that? We need to know how to code this first, right?
Yeah,
Coding is
yeah.
very important.
No, if you want to implement, yes, you have to be able to code it. So,
All right, sir. I'll post a discourse forum. I'll
oh,
post it on there
oh,
and let's see. Thank you, sir.
yeah, sure.
Sir, I have one question.
Yeah, please go ahead.
Sir, it is from week 4, PA2. Basically, I just want to discuss a different approach, like which we were studied in the PA2 question 4 of
One minute.
generating offsprings. Yeah,
Let me open the file. This week 4,
yeah.
yeah. Okay, yeah, go ahead.
So, sir, in that we have to generate offsprings using partial mapped crossover. Like we have P1 and P2 here, and if we want to generate C1 using location 6 and 10, which are BI and GO, bingo, and other nodes will be from P2, right, sir? So
Yeah,
what I was thinking, like in P2, we can write them write P2 members in our notebook, and like from 6 to 10 positions, like on sixth in P2 we have J, right? So we need B here for make it as a C1. So what I was thinking, like we can simply interchange like B to J, and then after on seventh position we have I, and in P2 we have A here. So we will just interchange A and I. So like from that approach, can we get C1 and C2 better way in this?
no, I did not catch your logic, so let me.
Okay. So
So is it that you're saying that you can swap some cities from P1 and P2?
yes, suppose I have to get offspring of C1, right? In C1, we will take 6 to 10 members of P1, else from P2, right, sir? So for P1 B, we have in sixth position in P2 we have J here. So for P in P2 we will simply swap B and J because we need B there. So sir is writing. I will explain it using that.
I hope I have copied it correctly. So, okay.
Yeah, it
So
is correct.
now we have a mapping here.
Yes. For generating C1, we need B and GO here, right, sir?
So let's see. Now what we are doing is, this is P1. is P2, and child 1, we are going to copy, and all these positions are removed.
Yes.
Okay. Now we have to fill up the remaining
These
values
positions.
for P2.
Yes.
Now the question is, you see B is already present,
Present,
right?
yes, so we
We are
can't
going to
take
pick
B
up,
from P2.
we
So
can
what I
take,
was
okay.
thinking, I can simply interchange these members in from P2. Like here we have J here, and we need a B here in P2, which we have here. So like we can simply swap them for better like approaching method. I was asking that. So we can write J here for C1 first
Where
J,
you're saying you can, yeah, okay.
and then N is also present there in third position, which is sixth, seventh, eighth. So we will swap
N
it
is,
with L.
okay,
L. So N and L will be swapped using in P2. So that way we will have L here.
okay,
For O, we have E here, and in P2 it is on third position O. So we will swap E and O in P2.
1 minute. Why should we swap E here? Because, see, we don't have, these 5 cities are occurring. So in the place of these 5 cities, we have to bring in other cities, right? And the remaining gets
Yes.
copied straight away as it is. So
Yes.
because B
Yeah.
is present, now we are trying to copy B from P2. We cannot copy because B is already present. So what do we copy here? Now we look at the mapping and say it is mapped to J,
J. Yes.
right? So J should
I
take,
think one
take
is
this.
exchanging within P2 itself. Like
Yes.
instead of within P2 itself, she's trying
Oh,
to
that's what you're,
swap
okay.
it.
Okay, okay.
Yeah.
Yeah,
I'm
so with
saying that
So
we take
that's why
P2
you
as it
use
is.
the word,
P,
okay.
she's swapping J. With
Okay,
N,
now you're
she's
putting
swapping
J
L.
here and you're putting B here.
Yeah.
Yes.
Okay. Let's see. I'll try and find a case where we can break that logic. Okay.
So have you tried it out on a few examples? Does it work?
Yes, sir. I tried it on two questions actually.
Okay. Now
That is
you
why
tell
I
me
was
what to swap.
so
Then I,
uh,
what
so
will you swap
we
I
need
with?
I here. I with
So,
fourth position. Yeah.
so this one, right?
Yes, sir. And we need N here. So we will
Yeah.
swap it with second node. Yeah.
Okay. Then how about K?
About K, we will
Oh, sorry,
replace it
not
with
sorry, not K. G.
G. Yeah. We will
G.
swap it with last member K.
Okay. So equal
Last
to
member of,
here and this
and we
one
will
here.
have K here. Yeah.
Okay. Then O.
And we need E here. So we will write E here. Yeah, O here.
Over here, there's
And
no
then as it
overlap
is.
in the alphabets. Maybe
Yeah.
we'll have to work with someone where there's an overlap to find edge cases. This
Yeah.
is working out beautifully in this.
One
Yeah.
Yes.
minute.
In this,
Development.
we
Let's
also tried on another question. Garima, do you have that question?
Space complexity would be lower in this, I guess. I mean, we were
Yes.
trying it on basically the previous year papers. In that, we were trying.
Yeah, we were trying
Should
on
I
that.
share the link?
Okay. So let us do this now. So
Yes, sir.
let us say let us construct another example. So stick with we'll do n here. What did I delete in the first step? So instead of a, let me put the n here. And now tell me, how will you work out? How will you do the swapping?
Okay, now if we need to generate C1, we will go
Even
to P.
one minute. Even J, I would remove.
Yeah.
So did we
So
lose
I have
something here?
shared the P1 and P2 for the crossover. They have overlapping for
Yes, they have overlapping
like
edge
if
case.
you want to try that. Yeah.
Okay.
Example.
So this is again another example from. This is an example from another paper, quiz one maybe, or
Yeah, 2023.
Yes.
Yeah. July 2023.
okay. I remember the alphabets here. So
We were going through the yeah previous year papers and yeah. so what is the mapping segment here?
CHEF 4 to 7.
Yeah. DGAH as well. Yeah.
Yeah, DGAH as well.
Yeah,
C
47.
H E F.
So if
Yeah.
this is a good algorithm, the space complexity will lessen in a way, right? I mean, we can.
Let us see. Okay. Now let's do the mapping. Now we have C, H, E, F. Now let's do the swap. Let's see. Do we get repeats here? C.
Yes.
What is repeating here? Tell me. I mean, C is not
So we
repeating.
will
Let us
uh,
H, E.
first we will have D
H
here.
is repeating.
H is repeated. Okay.
H
H is
is
the only.
repeating in both.
Okay. Hmm. Okay. We keep this aside for a moment because H is occurring last. Can you work with this one? Can you work with
Sorry,
this
sir.
one? Can you work with this one? Flame bingo.
Yes. Yeah, yeah.
With the one swapped. Say P2 I swapped. We have G repeating, N
G repeat.
repeating, okay, N
Yes.
repeating. Now let's see how will you B goes to G.
First, first
What?
we will need here B. So we will just swap it. So we will have G there in first position
Okay,
and B in this position. Yeah.
okay.
Okay. After that, we need I here in place of N.
Hmm.
So we will swap it with the I here. Yeah. After that, we need N here. So we will swap it with N position now, updated N position, which is fourth.
Hmm. So now this will
L.
go away.
Yes, we will have L here and then N here.
Okay.
Yes. After that, K. We need G here. So we have G on first position. We
Hmm.
will swap it with we will have K here instead of G now, and then G here in this position. And after E, we will swap it with third position. Oh, so now we have our answer. K. L
L,
BINGO HCFDJ. It would be our C1.
let's see, I have A, B, C, D,
It's quite interesting, but it looks like a variation of BMX in some sense.
I, J, K, L, M, N, O. Okay, each occurs only once, no duplicates.
Yeah.
This is very
That way
interesting.
we can like decrease the complexity of like repeating like if we miss
Hmm.
something.
About complexity, I'm not sure. We have to look at it closely. See,
Yes.
write down both approaches and see where the complexity is coming from.
Yes, sir.
Okay. Uh, but let us solve this one the regular way. You know,
Regular way. Okay.
sir, the way sir covers it in the class. I think you should publish this in some place as a variation. Not sure if they will accept it at least as a note or a
Okay.
small one-page, two-page paper. You should be able to publish it somewhere. Okay.
Okay.
Now, bingo, we'll put down bingo here. Okay. Now let's see. I want now the B has taken the place of G. So the way it goes is go from B to G. I'm trying to place G, but G is already present here. Then from G, go to K, right? Then where is K? Hold on. I lost the thread. Now to refresh the method now.
He was in the first position. I think you have mixed up the.
Now B is present. Now we have to find a goes like this from B go to G, G go to K, then K goes here. No, that is not right. I think I should go from G to B. That is also not correct. No, I have to review the method. Okay, I lost my train of thought.
We
Okay.
take like we will take F it is.
Okay, since B is there, to B's position, we need something. So I go from here. Okay, let me
Here to
recall.
here.
I'll go to G, but then look, G is also already present here. Now I'll go to G and then come back. Okay, I've recovered now. So this is how we do it. From B, B is already present. So in the position of B, I need something. Now go back to the mapping, get G. Now, but G is also present. Then go get K. Now K is not present. Therefore, I'll put K here. How about A? A is not present. Copy it. How about O? O is
O is
present. Go O here. Come
E.
down. E. And E is not present. So put E. And now I. Go from here to I. I points to N. But look, N is already present. Go back to N. Get to L. L is not present. Therefore, I put L here. Now M. M is not present. Copy. Then H is not present. Okay. H is not present. C is not present. F, I think the remaining is just straightforward copy, right?
Yes, sir.
Okay. Uh, Now, what is the solution you got? Your method.
Same.
Wow,
Same.
really nice. P1 star, this is new. Okay, this is from the lecture end.
Yes.
Okay.
Okay. Now, the next question is complexity. Okay, with the repeats, we are still getting the same, at least this example, we are getting the same result. Now, let's assume this is going to generalize.
Hi, Bhaskar, I need to go. Is that okay?
Yes, sir, sure, sir.
Okay, it was interesting
Thank
watching
you,
this
sir.
variation. Thanks, Muskan.
Thank you, sir.
And thanks, Garima. Okay,
Yeah.
bye.
Thank you,
Bye,
sir.
sir. Okay.
Thank you, sir. Have a good night.
So now let's count the number of lookups here. Say
Okay.
for B, we are picking up B here,
Hmm.
going into the mapping.
Mapping.
There's one lookup. Then I'm
One.
saying it is G. G is already present, so we have done some work here.
Hmm.
And so let's see. There is one plus. We have found out G is present, so we are going to do one more lookup, and
Yes.
then we fixed K. Okay.
Yeah.
For A, basically, we did a lookup for A to make sure it is not present.
Not present.
So for
Yes.
O, we made a lookup and then we picked up E and we have to make sure E is not present. So the same thing for K, it is not present. We have to make sure K is not present.
Three
So
lookups.
So wouldn't
three
it depend
lookup.
on the algorithm we are using to do it, like how we are approaching it, the number
Yeah.
of lookups?
Mm. See, store both in an array, store the mapping in a dictionary possibly. So this mapping, you can store it in a dictionary.
All right.
So let's say the mapping is stored in a dictionary, this mapping. See, this mapping is stored in a dictionary. Okay. Now let's see. So you pick up B, go back to B now. Erase this. Okay. Pick up B. Now this is in a dictionary. I do a lookup. There is one lookup here.
Hmm.
And then whether G is present or not already in the output,
Yeah.
in
Yeah.
the child. So I have to see whether G is present. G is not present. So basically there is one lookup for G to make sure it is not there in the child. Uh, In this case, we will find that it is there at the end of the lookup. Because it is present, now go back to the map and again do a lookup. Why the one is sticking close? Now you get K. Hold on. I pick up B, go to the map. Then this is map. This is child. Uh,
Map again.
then this is map. Uh, this is map for what?
For G,
B.
we are checking.
This is child and B. This is map. So I get to K. Then I have to say it's not
Check
present in
lookup. Yeah.
child. If it is not present, yeah, it is not present in this case. So we are settled. So we have done actually 4 lookups. Okay. But remember, the lookup in the child is if we maintain another map for the child, saying that how many values I've already inserted into child, say a set. In this case, we don't need a map, we can do a set. So child lookup is constant time and map lookup is also constant time. This is constant time. So 4 operations. Now A is you pick up A, then make sure it is not there in the child. There's only one child lookup here. For O, pick up, do a map lookup. It's first of all, you check whether it is there in child or not. Over that we have not done. So B is one child lookup. Sorry. See, to start, you pick up B and you see whether it is present in the child or not. If it is present, then go to the map and get G and check whether G is present. This is for B, this is for G, this is for G, and this is for K, this is for K. Sorry, one,
So
two, three,
for
four.
one lookup for child would be in each case either way for every one of the nodes, right?
Minimum one, yeah.
Yeah, so I think we can neglect that because that's a constant time. Like what
Yeah.
extra are we doing is
No, no,
more
no.
of a
Wait,
consideration. Okay,
wait. Yeah,
okay.
yeah. But you are comparing two algorithms, so you need to you will do n number of swaps when there is a duplicate. So we have to account for that.
Yeah.
Okay. Now when you do O, first
One
this
child,
is
one
child
map,
lookup.
one child. Yeah.
Okay, one map that will take us to E, and then you have to do a child and settle there.
Mhm.
How about I?
I is also
One
Present
child,
similar.
there.
one
Fifth,
map.
No, actually, it's no. I
it
is
is
going to N and then N is going to L.
mapping, and then
This is
again
I.
child,
This is N plus one child for N. That
and
takes
then
us to L, and L is a child lookup, and
and
that
then check.
settles. Yeah, that settles it. Now, how about M? M is straight away just one child lookup for M.
Mm.
Okay, and G
So
is already.
shouldn't it be five also like B, because it is going double again like B. I
B.
also going twice.
Hmm. Yeah, yeah. See, I am doing a child lookup.
Hmm.
I'm saying it is present. Then
Yes.
do a
After the N, you
map
map
lookup.
look up again. After the N child,
After
you're
L,
doing
we
the
have to
map
look up
look up.
I again.
Yeah, it would be five total. It's four over here.
No, L is child lookup, right?
And, so first we will
Oh,
check
yeah, yeah,
I.
yeah. I got it. Okay. Sorry. Okay. Mm, this will be a map lookup, you're saying.
Map look up and then child look up. Yeah.
Yes,
For
then
L
child lookup.
plus, yeah, one child lookup. That is when it settles.
Hmm.
Okay. Good. Now for map, it is just one child lookup. For G is present.
One
For
child
G,
look up, then
one
one
child
map look
lookup.
up.
No, we don't have to. When it is present, we just leave it. It is, hold on, G is, no, yeah, within the map, I don't have to do anything. Do I have to do anything within the map? Elements in the map?
They are already present there.
Yeah,
Hmm.
bingo, it's already present. But you have to make sure, since you're running through, you are only running through uh,
Every member once.
every member that is outside the map. So, and then you're, this is
All
one.
right, G is already in the map, so we don't go there.
So within this mapping segment, let's see.
Bingo
Things
and
within the
C. Yeah. Yeah.
this segment, we are not going to do a lookup.
Hmm.
Okay. Uh,
Hmm.
now, how many lookups we have done? One, two, three, four, five. So basically, we have 5 plus 1 plus 3 plus 5 plus 1
20.
plus 1, 2, 3, 4, 5. All put together 5. This is 15.
20.
Fifth, 20. Yeah. 15 plus 5, 20. Yeah.
Now, to your, the way
Hmm.
you swapped it, nice. So how did you do it? Okay. What is the implementation?
First, B and G will be swapped. One.
1 minute, 1 minute. See, in the child, you copy P2 to child, C1, right?
Yeah. P2 is copy.
Yes.
Yeah.
P2 is
Copy P2
copied
to
to
child.
C1.
Yeah.
Okay. P2 is copied. Okay. Assume it is copied. Uh,
Hmm.
now
Now
you
we
will
need,
swap
we will,
B and G.
yeah, we will go to sixth position directly, which we
Yeah,
need.
we'll go to 6% directly. Okay.
We
And
need
then we'll
B
say
there.
swap B and G.
Yeah.
There
So
would be around seven swaps, I
we
guess.
will check in list where we have B, and then we will swap it with sixth position.
Hmm.
So one
Okay. There is
lookup.
one swap. Okay. There is one. I mean, there is no lookup. You have to just swap. The lookup
I
is
mean
only with
Yeah,
test.
map position, right?
Yes, sorry.
yeah,
So,
yeah. In the
okay. Now, let's see. You do one swap. Mm, a swap contains what?
Hmm.
One read. Oh, it's a swap is what? Two reads and two writes, correct? Oh, we didn't do reads and writes there. So how will you compare
Are
one
we
page?
working with
The object
arguments?
such
What
yeah.
are we working with?
Okay, actually, we have to implement it and then see. Looks like uh, mm, there is one scan of P2 in both that is common.
Hmm.
Yes.
And then we have to write down the algorithm first. Then it will become easier to compare.
Yeah, pseudocode we'll have to write at
Yeah,
least.
pseudocode. Yes, yes. But this is a very
Hmm.
nice shortcut.
Yeah.
If
Thank
it
you.
works everywhere, then it's easy. Okay, I think
I
you
Certainly.
was
should.
thinking.
Okay, what I would
Sorry.
suggest is, what I would suggest is, you
Yes,
write
sir.
this down as an algorithm and
Okay.
send it to sir.
Okay. I will upload it on Discord and email
No, no,
to
you
sir
send it
also.
to send it to sir's email.
Okay. Okay.
Okay.
Okay.
So communicate with sir, say, and with some examples. Okay, where things are duplicated, and
Hmm.
show yours, and then also side by side show sir's method,
So sir's method.
or a few
Yes.
more examples. Pick up and write down the pseudo code, send it to him.
Hmm.
And
Okay.
subsequently, you look for, search the literature for such methods, see if there is a conference coming up where they're still dealing with these problems. These are all cold areas. When
Hmm.
Okay.
not many people are working, but still, if there is something different, they would encourage. So you can write it up as a two-page paper, abstract,
Okay.
intro of what is available, and then this is a variation on it. And if you can prove that this variation is doing exactly the same as the other one,
Yes, sir.
but slightly better. And then you have a
Hmm.
paper.
Okay. Thank you so much,
It's,
sir.
it's, it's
Yay.
publishable. But then it's a cold area, so
Hmm.
expect the unexpected. So
Yes, sir.
you will go with
Thank you for the guidance.
positivity. Somebody will come and say, no, no, this is not a big deal. This is not something you can complicate. So, but anyway, the effort is
Bhupendra
good.
has raised
Yeah.
the
I hope they accept it. But do it as a small paper. The chances of it will go as a note, two
Okay, sir.
page or at most 4 pages. So
Yes, I will do it.
yeah, okay, nice
Thank
discussion.
you.
Yeah,
Thank you so much, sir.
yeah. So you're the second candidate, probably in the last 12 months. I'm seeing there is one in the NPTEL course, search methods course, NPTEL version of it, uh, where a person came up with a nice improvement for I think DFID, and we already had that with us, but we didn't move, and he was
Hmm.
upset that we already knew it.
Oh, I'm glad, sir, I could come up
yeah,
with this.
so it did mention Sahil or somebody with that. So mentioned him, right, in the lectures.
No, 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 no. He's different. That is from IIT. I don't remember that.
Kharagpur,
Gauhati,
maybe.
no, Kharagpur, Gauhati, or someplace that
I
starts with.
saw Source lecture, yeah.
Yeah, yeah. Okay. So sir gives credit where it is due. So it's very open.
Bhupendra has raised his hand.
Yeah, go ahead. Ask.
Sir, can you explain the saving heuristics with any example?
Savings heuristic is such a simple, I would almost say silly, but people get confused. I don't know why.
I'm not able to solve the question, sir. I want to just an example.
Okay, let's see. Uh, Let me go back to the slide. Let's see. Where is Um, how do I locate the slide? See, there's a slide in the forum. What is the best way of locating it? On my machine or forum? I'm thinking which run I prepared it. With the first run, let me go sequentially. So this is which week? Uh, week 4? Is this from week 4?
Yes, sir. The question is in week 4, but it's in algorithm is in week 3.
Okay. Then it must be the slides folder. Slides. Okay. First term, it's not there. Assignment. How can you search easily, man? I don't even know the file name. Term, week 3, you said. Okay. Let's save it. Week 4. Come on. Okay. I think the best, easiest is to go to discourse, pull it from there. Take a screenshot. Keywords. Save button, problem. Here. Okay, I got it. So it was easier to get it from discourse. I got it. What is the big deal of science?
So the lecture is still streaming online.
Tell me.
Around 6 people. Publicly.
I don't understand. Tell me again.
Nothing, so sorry.
Okay. Okay. So what is the savings heuristic? So have you understood how the algorithm works, the basic idea?
Yes, sir. I understood, but I am not able to solve the question, sir. I just wanted any example.
Okay. Let us take this example. See, I don't want to give an answer directly. I'm trying to communicate the fundamental idea so that you will be able to solve that problem and other problems posed in savings heuristic. Okay.
Okay, sir.
So now there is a central node. In this case, it is A, right?
Mm-hmm.
Now every other node is connected to the central node via two loop path. The loop length is 2. Small loops, but each loop length 2.
Okay, sir.
Correct? So we have A, then we have B. Let me connect it this way. So there is no overlap. There is C. Then we have D and E. So how does a merge happen? And step 2, they're merging 2 loops. In this case, you see here, now you're merging. The edges selected for merges A, B, and AC, which means B and C will be connected. So the 2 edges selected are this one, AB and AC. Select. Now you connect B and C and drop these 2.
Okay, sir.
Got it. So the dropped edges Draw it like this. Now, what is the savings here? What did we save? There is cost of AB. We subtracted cost of AB. We dropped AB. We again dropped AC, correct?
Yes, sir.
And we added BC.
Yes, sir.
We added, this is plus, this is minus, minus.
Okay, sir.
Now this is the savings. What did I save here by making this change? The savings is for what? For introducing the edge BC. If I introduce the edge BC, then this is the savings I get. Now, instead of BC, I could have introduced the edge BD. Now, what is the savings here? Cost of BD minus cost of
AB.
AB minus cost of AD,
AB.
correct?
Yes, sir.
Then we could have introduced this, say, BE, and there's a cost of BE. You got the point. So,
Yes, sir.
the cost of AB minus cost of AE. This is the savings. Now, the central node is A, and there are nodes around it. Now we tried, say, can I introduce this? If I introduce this, what is the savings is the question I'm asking. If I introduce this, what is the savings? If I introduce this, what is the savings? So we have three savings values. Of these three, what is the highest savings?
Okay.
Pick that. Not only that, we could have started from C. I will show it as directional arrows. So we could have done C and then E also. And we could have done from D to E. These are all the possible savings for this problem. That's all. There are no more problems. So we could have done B with C, D, E. Okay. We could have done C with D, E. We could have, done D with E. So edges here. These are all the possible edges we can connect. Now, for each of this, you calculate the savings. So how many edges we have here? 1, 2, 3 total. So we have total 6. So you calculate the 6 savings values,
Okay, sir.
sorted in descending order. Descending order.
Hmm.
So highest, so you will get the savings like this: highest here and the lowest savings. Now start merging the edges. So what does a merge constitute? Merge constitutes dropping two edges and then connecting an edge between the peripheral cities. There is a central city which is A, and say, for lack of a better term, call the other cities peripheral. They are in the perimeter, on periphery, sitting on a circle, for example. Now you're always connecting those cities that are in the periphery, because all the cities are already connected to the central node. We don't have to reconnect them. You have to only connect those. And now you see, by doing one merge, now the loop grew. We took two small loops of length 2 each, and then we constructed one bigger loop of length 3. Now we have 3 loops. After this, now let us follow the problem here. The next merge is CE. Next merge is CE in this case.
Yes, sir.
Okay. So when you merge CE, instead of cutting across, I'll put the edge like this, for example. And these two have to be deleted. Now what do we have? How many loops do we have now? This is minus. This is minus, and this is plus. So we have two loops. One is A, B, C, E, A, back to A. That's loop of length 1, 2, 3, 4. Loop of length 4, and there is a small loop which is AD. Now, according to the slide here, next is D and E are merged, which means you take, oh, wait a minute. D, C and E are merged, add CE, we are done. Then add DE. So we have to connect here. Yeah. So now this becomes, you drop this, one, and you drop this, right? So we drop this one and this one, and we are going to add this one, plus. Now you see we have a single loop.
Okay.
So this single loop is a tour. This is the biggest tour. So now we stop. Algorithm stops. It's plain simple. I don't know why people are getting confused. And it can be stated in a single slide. No complexity at all. See, the idea is this. The big idea is this. In forum, we have several posts on this. The big idea is this. We have loops of length 2. The idea is to keep merging this small loops into a bigger loop. How will you do that? The central node is not going to change. So this is a node n, central node. And then you have A, B, C, and dot, 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 whatever. And now all the peripheral cities are connected to the central city. So there is no issue between their connections. In fact, there are excessive connections. Now you keep removing the excessive connections and then start connecting the peripheral nodes. That is the idea. Now, which peripheral nodes to connect? Pick the one with the highest savings. Got it?
Okay, got it.
That's all. It's very simple. Now with this, you must be able to, let me bring.
Okay, so I'll try.
It's very simple. Some people catch it, but most people, they're not watching the video properly.
The time is so actually we don't get time to
So
study.
that's your problem, right?
Yes, sir. Managing family and office and
No,
this.
no, no. See, that you cannot give as a reason at all. That's common for everybody. If you're trying to do an extra course, which means you're ready to take extra burden.
Yes, sir. It's my choice.
Oh, you cannot say, yeah, you cannot say this. It's your choice. And you better pull through. So we cannot change a course. See, the idea is to build a community who are knowledgeable in the subject, not knowing answers, just write the exam, pass and go. But people who understand how to read an algorithm, how to implement it, how to change it. For example, today's discussion on the PMX was really nice. Sir will be very happy. I think he will mention the candidate in his future talks. So he's going to do that. It's a really nice variation. So that's thinking. We appreciate that. We want people to go there, think. So in this savings heuristic, this part of the algorithm builds the initial structure with n minus 1 tours, each of length 2, anchored at a app city n, here small n, let me say small n. Capital N stands for number of cities. It's overloaded. And now savings list is empty, and then you're doing n into n plus 1 by 2 combinations here. And you see, what is the savings? Okay. The savings is, I put the other way around, sorry. Savings is, what am I saving? This is the cost included. This was the original cost. That is, these two columns are present, currently present, because we have not done any merge. And this is what we are going to add. I mixed up the signs. Between the, if you do the other way around, take the cost of a state, then merge it. After merging, what is the cost? Then do subtract both, and that's what you save. If you do that, and this is the expression you would get for savings. Okay.
Okay, sir. I'll try.
Okay. And you construct the n into n plus 1 by 2 savings values. So many edges are possible. This not just n, sorry, one, we have selected 1, so only n minus 1 cities are there. So it is n into n by 2, not smaller. So these many pairings you will get of the peripheral cities. This is the pairings for the peripheral cities. You calculate the savings, then sort it in descending order, and now start merging. Now every merge is not possible. Suppose you have A here, B, C, and A, for example, and there is one loop here, another loop here. It's a different problem. C, D, E, F, for example. Now, will you merge B with F now? Yeah, it's possible. Correct? I can merge B with F. I can delete these two. Now, will you merge B with D? Is this
B with
possible?
D. No, sir.
No, it doesn't make sense. So you have not merged two loops into one, right? You cannot. So there, these conditions you have to take care. You have to make sure that when you're merging, you're always progressing towards preparing a big loop, bigger and bigger loop, right? So you cannot merge this one with D because it will form a fork, and in a tour there is no fork. So you have to manage those conditions, right? And that's what it says here. And these conditions are stated in such a way that uh, that the mergers make actually a progress towards constructing a tool and not create forks and other things. The conditions are stated in such a way that it avoids forks and so on. So read that condition. You will see mathematically it will avoid forks. Okay.
So, this meaning of edges N A and N B belongs to two subtours.
Two different tours, right? So let's see. Uh, if I take AC and AF, it has this form. N goes to from the central node N, it goes to A. From central node N, it has to go to B. Two edges have to pick. You see from this pattern matches A to C and A to F. And if CF happens to be the current good best savings current as of now, as of this state, if it is best, will you remove these two and connect F and C?
No, sir.
It doesn't make sense, because now A is not connected to, you are now forming two disconnected loops. You can't do that. So therefore, the condition says that you pick from the central node, you pick two edges and go to A and B, such that these two edges are part of two different loops. So which means I cannot pick this edge because this does not originate from the central node. This edge is also out of question. I cannot pick up. It's not originating from the central node. So the edges that qualify are 1, 2, 3, 4, 5, 6. Of course, 2 and 3 are duplicates, 4 and 5 are duplicates. So if I pick 1, then definitely 6 cannot be picked. If I pick 1, then 2 can be selected. Or 2, 4, or 1, 3, whatever. Barring duplicates, I have only 2 other choice. Then say if I pick 2, then I cannot pick 3 because it's a duplicate. I can only pick either 4 or 5. Right? So these things you have to make sure happens correctly, and the algorithm is stated in such a way that it will happen correctly. Actually follow those rules. It took some time to define it and define it in a way that it takes only one line to do. So I went through several revisions to bring the algorithm to this form. All the conditions are included. So if somebody implements it, it'll run correctly.
Okay.
Okay. So that is savings heuristics.
Okay,
It's
sir.
one of the practically useful heuristic for TSP. It's really nice. But it does not guarantee optimal solution. But it goes close. Okay, what it is 8:52, 2 hours now. So if you guys have any questions, we'll address it. Otherwise, I have a deadline 5 for knowledge representation and reasoning. So I have to release week 5 assignment. Practice assignment is ready, the graded assignment. Still preparing. Other 4 more questions to go.
Okay, sir.
Okay. After that, quiz 2 paper I have to prepare. There's so many things on my plate.
Okay, sir.
Okay.
Okay.
Yeah.
Can we discuss?
So, okay. Yeah. Thank you, guys.
Thank you, sir. Bye.
Okay. Thank you. Bye.